viewers, we are pleased to bring to you another program in Teleschool Senior Series. The subject today is complex numbers. As you are aware that complex numbers have recently been introduced in the A-level syllabus. We hope that this program will make the complex world simpler for you. Let's see, why do we need complex numbers? Why do we need to study more numbers? Why real numbers are no more sufficient? Consider the following equation. X squared plus 1 equal to 0. Whenever you are asked to solve this equation, you will get the solution x equal to plus minus root of minus 1. And we used to stop here and say that, well, the solution is not real, so we stop here. Now, mathematicians realize that we need to accommodate solutions of such equation. And that's why they enlarge the real number system to the complex number system. Let's see. The real number system consists of the rational numbers and irrational numbers. And the complex number system consists of real numbers and imaginary numbers. So, the complex number system has the real number system, which you are used to, and the imaginary numbers. So, let's define a complex number. What is a complex number? A complex number is a number which has the following form. Z equal to x plus iy. So remember, this is the form of a complex number, x plus iy, where x and y are real numbers and I is defined as square root of minus 1. This is a new symbol, I, square root of minus 1. X is also called the real part of complex number z. Y is also called the imaginary part of z. We write x as REZ and y as IMZ. Examples of complex numbers would be 3 plus 2i, 1 minus I, half plus 5i, and 2i. 3 plus 2i, the real part is 3, the imaginary part is 2. In 1 minus I, the real part is 1, the imaginary part is minus 1. The real part is half, the imaginary part is 5. And in 2i, the real part is 0, the imaginary part is 2. This number, in which the real part is 0, will be called purely imaginary. It is also useful to note that since I has been defined as square root of minus 1, I squared will be equal to minus 1. I cube will be equal to minus I power 4 will be equal to 1, and I power 5 will be equal to I. And using this definition, we find that from now on we can write square root of minus 1 as I, square root of minus 4 as 2I, square root of minus 9 would be 3I, and square root of minus 5 would be square root of plus 5I. Therefore, we see that we are now able to accommodate imaginary numbers and solutions of equation of the type x squared plus 1 equal to 0. It is very useful to represent a complex number by a point in a plane. And that plane will be same as the xy plane, but we are going to call it the Argon diagram after the great mathematician Argon. Let's see. We still have the x and the y-axis, but we are going to call the x-axis as the real axis and the y-axis the imaginary axis. The complex number 3 plus 2i, which has real part 3 and imaginary part 2, would be represented by the coordinates 3, 2. 3 real, 2 imaginary. Similarly, the complex number minus 4 plus I, which has real part minus 4 and imaginary part 1, will be represented by the coordinates minus 4, 1. Same applies to the complex number 2 minus 3i, represented by 2 minus 3. minus 3 minus 4i represented by minus 3 minus 4. Also note that if I have two complex numbers, a plus ib and p plus iq, the two complex numbers will be equal if and only if the two real parts are equal. That is, a is equal to p and b is equal to q. Every complex number has an associated complex number called its conjugate. Let us define what is the conjugate of a complex number. The complex conjugate of z of a complex number, say z is x plus iy, is defined as x minus iy. The complex conjugate of x plus iy is x minus iy. If we are representing the complex number by z, then we'll represent the conjugate by z bar or z star. And you must have noted that z and z bar are reflection of each other in the real axis. Consider the following complex number 3 plus 4i. Its complex conjugate will be 3 minus 4i. That is, to obtain the conjugate, we multiply the imaginary part by minus 1. Half I will have a complex conjugate of minus half I. Can you guess what would be the conjugate of 5 minus I? The imaginary part is minus 1. I'm going to multiply minus 1 by minus so that we get 5 plus I. The complex number half minus 1/8 I will have a complex conjugate of, here the imaginary part is minus 1/8, which we multiply by minus 1 to obtain plus 1/8. It is also useful to remember the following. If z and z bar are pair of complex conjugate, then the real part is obtained by adding the complex number z and the conjugate and dividing the sum by 2. The imaginary part is obtained by subtracting z bar from z and dividing the difference by 2i. Note that we also call the following as pairs of conjugate. 3 plus 4i and 3 minus 4i are often referred to as complex conjugates. Complex numbers also have the following property, the modulus. Every complex number will have the modulus or the absolute value. Let's see how to define the modulus or absolute value of a complex number. Modulus of a complex number is defined as the square root of the sum of x squared plus y squared. That is, the real part to the square plus the imaginary part to the square, we take the square root of the sum. 3 plus 4i, the modulus of 3 plus 4i will be obtained as follows. 3 to the square plus 4 to the square and square root, which gives us 5. Let's see how to find modulus of 1 minus I. Square root of, the real part is 1, 1 to the square. The imaginary part is minus 1 to the square, so that we obtain square root of 2. The modulus of 4i, which is a purely imaginary number, will be obtained as follows. The real part is 0, 0 to the square. Imaginary part is 4, 4 to the square. The square root of the sum, which gives us 4. What does modulus mean? Modulus is the distance between the origin and the point. For example, modulus of 3 plus 4i is 5, means that the distance from the origin to the point 3 plus 4i to the complex number 3 plus 4i is 5 units. It is very common to represent modulus of a complex number by the letter r. And it is useful to remember that modulus can also be obtained by taking the square root of the product of the complex number and its conjugate. Complex numbers also have another property, the argument. Every complex number will have an argument. Let's see how to find the argument of a complex number. Argument of complex number z, we write it as argz or arg x plus iy. And suppose that it is theta. The complex number will have an argument theta, means that the angle between the positive x-axis and the line joining O to Z is theta. Remember, argument is defined as the angle between the positive x-axis or the positive real axis and the line joining the origin to Z. And argument must have a value between minus pi and pi. Let's take examples and find argument. To find argument, the first step is to locate the complex number in an Argon diagram. The next step is to use the formula tan inverse. We have four complex numbers here. Z1, which is 1 plus I, Z2, which is minus 1 plus I, Z3, which is minus 1 minus I, and Z4, which is 1 minus I. Let's find the argument of the complex number 1 plus I. The argument of Z1 would be the angle between the positive real axis and the line joining origin to Z1. So this angle will be the argument of Z1. And since the length is 1 unit and the height is 1 unit, and tan inverse of 1 is pi by 4, therefore it will have an argument of pi by 4. We say that the complex number 1 plus I has an argument of pi by 4. What is the argument of minus 1 plus I? It is the angle from the positive x-axis to the line joining origin to the complex number. So this is the angle. Since this angle is pi by 4, because this is 1 unit and 1 unit, so tan inverse of 1 gives us pi by 4. Therefore, this angle will be the argument of Z2 and equal to pi minus pi by 4, which is 3 pi by 4. Similarly, what is the argument of minus 1 minus I? It is the angle from positive real axis to the line joining origin to the complex number. Now, you know that I have taken the angle in a clockwise direction because argument cannot be more than pi radian. So this angle is the argument of Z3. We know that this angle is pi by 4. Therefore, the argument will be given by pi by 4 minus pi, which is minus 3 pi by 4. The argument is negative. Argument of minus 1 minus I is minus 3 pi by 4. Similarly, the argument of 1 minus I would be the angle between the positive real axis and the line joining origin to the complex number. The angle would be given by minus pi by 4. Minus because we have taken the angle in a clockwise direction. Therefore, note that all these four complex numbers have the same modulus, root 2, but their arguments are different. All these four have the same modulus but different argument. Therefore, it is very important that whenever you have to find argument, you locate the complex number on an Argon diagram and then find the argument. Complex numbers can also be added, multiplied and divided. Let's see how to add two complex numbers. Suppose that we have complex number z1, which is a plus ib, and complex number z2, which is c plus id. To add z1 and z2, that is to add these two complex numbers to obtain another complex number, and to add the two complex numbers we simply have to add the real parts, a plus c, and add the imaginary parts, b plus d, so that we obtain a plus c, this is the new real part, and b plus d, which is the imaginary part. Let's illustrate that by an example. Suppose z1 is minus 2 plus 3i and z2 is 1 plus 2i. To add the two complex numbers, we add the real part, minus 2 plus 1, which gives us minus 1. We add the imaginary parts, 3 plus 2, which gives us 5i. So, minus 2 plus 3i plus 1 plus 2i is minus 1 plus 5i. Let's see how to subtract two complex numbers. z1 minus z2 is given by the difference between the real part and the difference between the imaginary part. So, z1 minus z2 will be given by a minus c and b minus d. Let's take an example. If we have to perform minus 2 plus 3i minus 1 plus 2i, we proceed as follows. Minus 2 minus 1, difference of the real parts. 3i minus 2i, 3 minus 2, which is 1. Minus 2 minus 1, minus 3. 3 minus 2, 1i. So, to add complex numbers or to subtract complex numbers, we add real parts and imaginary parts, or subtract real parts and imaginary parts respectively. Let's see how to multiply two complex numbers. Suppose I have to multiply a plus ib and c plus id. To multiply, we proceed as if we are multiplying the elements of the two brackets. A times c. A times id. So I obtain ac plus a times id, I ad. B times c, ib c. ib times id, I squared bd. Note that I squared is nothing but minus 1. So that we have ac minus bd. We remove the I outside to obtain I ad plus bc. Rearranging, that is grouping all the real parts together, we have ac minus bd and I ad plus bc. Let's illustrate that by an example. Multiply the two complex numbers, minus 2 plus 3i and 1 plus 2i. To multiply, we multiply minus 2 and 1 to obtain minus 2. Minus 2 times 2i, we obtain minus 4i. 3i times 1, we obtain 3i. 3i times 2i, we obtain 6i squared. I squared, remember, is minus 1. So that we have minus 6. Minus 4 plus 3i gives us minus I. Minus 2, minus 6, minus 8, minus I. So, product of minus 2 plus 3i and 1 plus 2i is minus 8 minus I. To divide z1 and z2, for example, if you have to divide a plus ib by c plus id, the first step is to multiply both numerator and denominator by the conjugate of the denominator. Note, the denominator was c plus id and the conjugate is c minus id. So we multiply the numerator and the denominator by the conjugate of the denominator, and we multiply as shown to you above, so that we obtain the following: ac plus bd I bc minus ad over c square plus d square. Let's illustrate that by an example. Divide minus 2 plus 3i by 1 plus 2i. To divide, the first step is to find the conjugate of the denominator. The conjugate of 1 plus 2i is 1 minus 2i. We are going to multiply the numerator and the denominator by the conjugate of the denominator. Multiplying minus 2 plus 3i, 1 minus 2i, and 1 plus 2i and 1 minus 2i, we obtain the following: 4 over 5 plus 7 over 5i. So, we have seen how to add complex numbers, subtract complex numbers, multiply and divide complex numbers. Now, let's see the most important part: how to use complex numbers to find the solutions of equation. There is an important property that you have to remember. All the polynomials which have real coefficient and which have a complex number as a root will also have its conjugate as the root. That is, if you have complex root, they must occur in conjugate pairs. That is, if 3 plus 4i is a root, then 3 minus 4i must also be a root of a polynomial with real coefficient. So let's illustrate that by an example. If we are asked to solve x squared minus 6x plus 10 equal to 0, it's a quadratic equation, so we'll use the quadratic formula. Applying the quadratic formula result in 6 plus minus square root of minus 4. Now we know we can handle the square root of minus 4. It is nothing but 2i, so that we write 6 plus minus 2i divided by 2. We obtain 3 plus minus I, which is 3 plus I and 3 minus I. So note that 3 plus I and 3 minus I are the complex conjugate. We have 3 plus I and 3 minus I. These two roots occur in conjugate pairs. If 3 plus I is a root, 3 minus I must also be a root. Complex numbers also have two other important forms. Up to now we have seen that all complex numbers were written in the form x plus iy. There are two other important forms called the polar form and the exponential form. So if r is the modulus of the complex number z and theta is the argument of the complex number z, then x plus iy, the one that we are used to, the complex number, can also be written as r cos theta plus I sin theta. This form will be called the modulus argument or simply the polar form. We can also write x plus iy in the form r ei theta, which is the exponential form. Let's see how to convert between the usual form and polar form and exponential form. How to write root 3 minus I in polar form and exponential form. Note the real part here is root 3 and imaginary part is minus 1. So the modulus of the complex number would be given by root 3 to the square plus 1 to the square, which is 2. And the argument is minus pi by 6. To write it in polar form, we replace r by 2 and theta by minus pi over 6. So that root 3 minus I is nothing but 2 times cos theta minus pi over 6 plus I sine minus pi over 6. So this is the polar form. The exponential form can be written as follows. We just replace r by 2 and theta by minus pi over 6. So root 3 minus I is one form, 2 cos minus pi over 6 plus I sine minus pi over 6 is another form, and we have the third form, the same complex number written in 3 different forms. You must be able to convert from one form to another. There are various advantages of using the exponential form. Let's take the first one. If I have to find z power n it is sufficient to write the polar form and take the power n. Similarly, in z power n, in polar form would be Rn cos n theta, I sin n theta. Let's illustrate that by an example. If z is 3 minus 4i, find modulus of z, argument of z, and z power 20. Modulus of z will be 5. Argument of z is minus 0.927 radian. Therefore, z power 20 will be 5 power 20, I 20 times minus 0.927. That is, we have just replaced r by 5 and theta by minus 0.927 and n by 20 to obtain the following. Remember that argument must always be between minus pi and pi, so that we have to give the argument between these limits so that it becomes 0.35i. So the exponential form is very useful if you have to find powers of z, z power 5, z power 20. Let's see what will be the modulus and argument of a product of two complex numbers. We find that if z1 is r1 ei theta, z2 is r2 ei phi, then the product z1 times z2 will be obtained as follows: r1 r2 exponential I theta plus phi. This means that the modulus of z1 plus z1 times z2 is nothing but r1 times r2. That is, remember, modulus of a product is product of modulus. That is, product of modulus of z1 times z2 is modulus of z1 times modulus of z2. Similarly, the argument of z1 times z2 would be argument of z1 added to argument of z2. That is theta plus phi. Similarly, we can find the modulus of z1 divided by z2. Modulus of z1 divided by z2 is exactly equal to modulus of z1 divided by modulus of z2. Argument of z1 divided by z2 is argument of z1 minus argument of z2. Let's illustrate that by an example. If we take the two complex numbers z1 and z2 as follows: minus 1 plus I and 3 plus 4i, which have, the first one has modulus root 2 and argument 2.356 radian. The second complex number has modulus 5 and argument 0.927 radian. We want to have the modulus of the product without multiplying z1 and z2. So using the previous formula, modulus of z1 and times z2 would be the product of modulus of each. So it will be root 2 times 5, 5 root 2. What would be the argument of z1 times z2? It is the argument of z1, 2.356, added to argument of z2, 0.927, which gives us 3.283 radian. Again, remember that argument must be between minus pi and pi, so that it becomes minus 3 radian. So without multiplying the two complex numbers, we have been able to find the modulus of the product, 5 root 2. The argument of the product, minus 3 radian. Similarly, what would be, without dividing z1 by z2, what would be the modulus of z1 over z2? Using the previous formula, it would be the modulus of z1 divided by the modulus of z2. That is root 2 divided by 5. What would be the argument of z1 over z2? Without dividing z1 by z2, we know that argument of z1 over z2 would be argument of z1 minus argument of z2. which gives us 1.429 radian. Now, it is also very useful to remember the geometrical interpretations of the operations. What does addition of complex numbers mean? Addition of complex numbers is equivalent to a translation. That is, adding W to Z is equivalent to translating Z by P plus Q. Let's see it clearer on this diagram. This is Z, complex number x plus iy, and W was the complex number P plus iq. Adding W to Z is equivalent to translating Z, so that Z plus W becomes x plus P, y plus Q. Similarly, subtraction of complex numbers is equivalent to a translation. That is, Z minus W is equivalent to a translation by minus P minus Q. Let's see it clearer on this diagram. Z minus W, Z was x plus iy or xy on the Argon diagram. Z minus W is x minus P, y minus Q, which is a translation. Similarly, multiplication of complex numbers has a geometrical interpretation. Multiplication of complex numbers is rotation followed by an enlargement. Let's see. Multiplying Z by W is equivalent to rotating OZ through angle phi about center origin, followed by an enlargement with scale factor R2 and center origin. Let's see it clearer on this diagram. We had Z and we had omega. Multiplying W and Z is equivalent to rotating Z through phi and enlarging it by scale factor R2. In both cases, we take the origin to be the center. So that if this is Z, this is W, we have the product of the two as the following complex number. It has an argument of theta plus phi, where theta was the argument of Z and phi was the argument of W, and a modulus of R1 times R2. Similarly, division of complex numbers can be geometrically interpreted. Interpretation: geometrically, division means a rotation followed by an enlargement. Dividing Z by W is equivalent to rotating OZ through minus phi. Note, phi is the argument of W. We rotate by minus phi and enlarge it by a scale factor 1 over R2. Let's see it on the following diagram. We have Z, which has argument theta and modulus R1. We have W with argument phi and modulus R2. Z divided by omega will have an argument theta minus phi and a modulus of R1 divided by R2. So division is equivalent to a rotation through minus phi and an enlargement with scale factor 1 over R2. Now, if Z is a variable and OZ is the line joining the origin to Z, we can sketch the locus of Z under certain condition. Let's see the first condition. What is the locus of Z, of the variable Z, if modulus of Z minus A minus IB is equal to R? The locus will be a circle. Center A plus IB, radius R. The second condition. What is the locus of Z if argument of Z minus A minus IB is equal to theta radian? Locus of Z would be a half line. Note that the line is not continued. It's a half line making an angle theta with the line passing through A plus IB. So the locus of Z would be a half line making an angle theta with the horizontal line passing through A plus IB. The third condition. If Z equal to A plus IB plus lambda P plus IQ, then locus of Z would be a line passing through A plus IB having gradient Q over P. Let's see the fourth condition and the fourth locus. If modulus of Z minus A minus IB is equal to Z minus P minus IQ, then the locus of Z is the perpendicular bisector of the line which joins A plus IB to P plus IQ. So the locus of Z is this perpendicular line of the line joining A plus IB to P plus IQ. The fifth condition. Argument of Z minus A minus IB over Z minus P minus IQ equal to theta radian. The locus of Z is an arc of a circle joining A plus IB to P plus IQ in an anticlockwise direction, such that the chord which joins A plus IB to P plus IQ subtends an angle theta. So that if you have A plus IB, P plus IQ, then the locus will be an arc of a circle such that the chord subtends an angle theta. So we have now reached the end of today's program. We have seen the different aspects of the world of complex numbers: definitions, properties, conjugates, modulus, arguments, geometrical properties, and locus. Thank you for watching this program. Should you have any question or suggestion, we invite you to write to the Mauritius College of the Air on the following address: Telemail, Teleschool Senior, Mauritius College of the Air, Réduit. You can give us a phone call on 403-8200, or you can also visit our website on the following address: mcawebcast.org. We would like to thank the production team of the MCA and of course you viewers for your kind attention. Until next time, it's goodbye from us.